Very good evening, everyone, and welcome to the Bangalore Theory Seminar. I have the pleasure of introducing today's speaker, Professor Tobias Mömke. Tobias is a professor of theoretical computer science at the University of Augsburg. He obtained his PhD from ETH Zurich and followed it up with postdocs at ETH, KTH Royal Institute of Technology, Sweden, and Saarland University. After spending a few more years at Saarland as a PI and then a group leader, he joined at Augsburg as a professor. His research aims to develop new algorithmic approaches for optimization problems with limited resources, and he has made some significant contributions in the fields of online and approximation algorithms. Today, he will be talking to us about his recent work, a PTAS for Unsplittable Flow on a path. So without any further ado, I'd like to hand it over to you, Tobias.
Thank you very much for the introductions. Wait a minute, I'll share the screen. Yes, today we'll be talking about a problem called Unsplittable Flow on a path, and there we obtained a polynomial time approximation scheme. And the last step of the work was joint work with Fabrizio Grandoni and Andreas Wiese. Those guys also have been on this problem since a long time, as well as I have been, but many more people were involved, and this we will reveal during the talk. So first of all, I start with this image here. And what is this? This is, a while ago, I have been to Paris. In Paris, you find all kinds of street art that sort of looks like this picture. We'll reveal later on what the relation is to this talk, but there are actually like quite a few nice subtle like parallels. For once is you have all these tiles, and you will see lots of squares within this talk. But first, let's define the problem that we will, that we studied, that we will be talking about. It's called Unsplittable Flow on a path, or some people prefer to call it all or nothing flow, because the name comes actually from general graphs, where it makes more sense in a way. And then the special case for the line, which is a really well-studied and really important case, just carried on the name. But I mean, you will see where the name is coming from after I introduce the problem. What are we given? We're given a path P. So here we have this path P that is, imagine a timeline, and we discretize the timeline into a path. Next, we are given a capacity U for each edge. That means if we have any edge here, we have a capacity UE. And well, this curve is just a smooth curve, but you can just discretize the curve, so that doesn't really make a difference. Now, what do we want to do? We want to schedule tasks. The tasks are like listed down here. What do we want? We want to move those tasks under this profile, and we do not want the profile to be exceeded. So how is the task characterized? The task has a start point. That is this S. So if this is task I, then we have here our start point Si, here our endpoint Ti. Then we have a wait and a demand. So the wait is just a number because we want to maximize the wait, the gain that we get. And then the demand is like how much capacity is actually consumed by this task. The goal is to schedule as many or as high value tasks as possible without exceeding the profile. So it looks like this. This would be a feasible solution because you can see that we have this profile and all tasks are underneath the profile. So you might say, okay, we have a problem here. I claim we do not have a profile problem. Why? We define the problem in such a way that the sum of demands should be lower than the capacity. And here you see there's still free space. So that is, we can push the task down, and therefore, well, it doesn't matter that the task is like higher here than here. So therefore, this would be a feasible solution to the problem. So now back to the names, all or nothing flow. I mean, we have to schedule a task completely or not at all. And unsplittable flow makes no sense if we have a graph where there is some splitting going on. There we have to really choose one path of the options, and we cannot split the flow through several paths. But I mean, if we have just a line, then we still have to either schedule the whole task or nothing at all. Now, this red task cannot be scheduled anymore because, well, this would really exceed the capacity. And unsplittable flow is related to like several problems that we all know and love, like the knapsack problem. So knapsack problem, recall we have a certain capacity B, and then we have these items, which we can also see as tasks. Each item has a demand, and we can have a weighted version where each item has a weight. And we want to maximize the weight of items as to not exceeding the capacity. And if you paid attention on the last slide, this is the very same setting as UFP, except that we only have one edge. That means knapsack is a special case of UFP on a single edge. And from that, you can also directly see that UFP is NP hard. And well, for knapsack, we know there is a 1 plus epsilon approximation, or in other words, there is a PTAS. There's even an FPTAS for knapsack. So, and now the question is there also PTAS for UFP? Because UFP is, of course, much more general. And that was a long journey to actually get to the PTAS that we, in the end, obtained here. There are some other problems that are somewhat related. So in knapsack, you see we have only one edge, and then there is a second dimension from left to right. And such problems can be have been seen in the literature before, like the two-dimensional knapsack problem. That means we have the normal knapsack problem where we have these items, but these items are rectangles. And now we want to pack those rectangles inside of this square or rectangle here, and then we can actually move it to all sides. And it's a geometric problem. We cannot break this rectangle apart. For that, there is a 4/3 approximation where some of my co-authors were authors of that paper, but I was not part of that. Then
so,
independent.
one comment. So this 1.33 is pseudo polynomial time. For polynomial time, the best is 1.89 for 2D knapsack.
Yeah, thank you for the comment. And then a second problem that is sort of also in the two-dimensional space, but on the other extreme is we have, again, these items here, but each item is locked in place, so we cannot move things around at all. And then we have to choose a subset of those items such that they do not overlap anymore. We want to maximize the weight of the subset that we choose. And this problem is called independent set of rectangles. And for that, last year, we obtained a 2 plus epsilon approximation. That means the first constant approximation was obtained a bit earlier. And we were able to push the techniques quite a bit to get the 2 plus epsilon approximation for this problem. Now we come closer to the problem that we study. On the right-hand side is unsplittable flow, as I presented it already. There's also a geometric version of this problem on the left-hand side, where we have a problem that is sort of like two-dimensional knapsack, two-dimensional knapsack, but we can move tasks only up and down and not left to right. And of course, this profile is slightly different. For that, there is a 1.969 approximation that we obtained a few years ago. So the interesting part is here you can see really the difference. A task can be scheduled if you can somewhat push it down, if really the sum of demands does not exceed the capacity, whereas here you really have to put the geometric object into the picture without overlapping, and then this geometric object should not violate the capacity. UFP also has some nice applications. And one application I find particularly interesting, that is you take a satellite. So what does a satellite do? A satellite orbits around the world. And then, of course, that's not enough for us. We have to satisfy several tasks. So we want to communicate. So there are certain points on the Earth's surface where the communication can take place. And of course, we want to somewhat send or receive things. So we want to maybe take pictures or record some tokens from some airplanes, things like that. That means, say, we want to record some data from this landmass in this strip of the Earth. Then we have to do this while the satellite is within this green area here. And what does it mean? We have a specific starting point where the recording starts and a certain end point where the recording ends. And if we do not comply with this timing, we don't have a proper recording. So this actually models pretty well that we have a task that has a specific start and end time. And now what's the demand? Different tasks done by the satellite have power demands. So you need electrical power to run those tasks on the satellite. At the same time, you have a certain capacity that changes over time because you are exposed to the sun and the satellite has solar panels. The application is slightly different because we also have batteries that somehow change the things around. But like based on the ideas and techniques for UFP, I was involved in an experimental study that was really running schedules for real satellites, where we actually showed that in this very simplified setting for satellites, we actually had an executable running algorithm that was computing schedules for the satellite. Yeah, of course, lots of different applications beyond satellites, like bandwidth allocation. So you have a certain bandwidth for some radio transmission that is needed for a certain period of time by, say, some company. They can buy it or not buy it, but they only buy it if it's at this in this time interval. So you want to maximize the profits that you get from the bandwidth that you have. Or caching. You want to execute programs. You have only a limited amount of fast memory. So therefore, you have to reserve a memory block for a certain period of time, and that the amount of memory that you have gives you a capacity. Or in logistics applications, you also quite naturally come to UFP-like settings.
So I have one question.
Yes.
So in the previous slide, so in UFP problem, we are not allowed to move the jobs side by side, side to side, is it?
Yeah, that's right.
Okay, so my question, like, how does 2D geometric knapsack fall under this case? Because in that problem, we are allowed to slide objects side to side, right?
Yes, it's like that was an example for a related problem, but it's of course not the same problem. So, I mean, we have objects that we move around and that should not overlap. And that's the case also like the direct relation is to storage allocation, where we can move objects up and down, but not left and right. So that's sort of the only difference. And then independent set of rectangles is the other extreme, where we are not allowed to move them at all.
Sure.
But of course, it's not the very same problem. So to get started on how to approach UFP, we first look at simplified cases. That is, we look at the case where all tasks are small and the case where all tasks are large. So for that, let's introduce some notation that we might use several times again in the talk. We have a task I, then P of I is a subpath of that task. That means, recall we have a start and end time, and then there's a path from the start to the end, which is a subpath of the overall path, and we call this P of I. And then a task is small if the demand is smaller or equal epsilon times the available capacity for each edge in the path, and it's large if there exists an edge where the capacity is at least epsilon, or larger than epsilon, the capacity. So to make this a little bit more easy to understand, we also have a picture for that, and we have the notion of bottleneck capacity. That is, if we have this task I here, it has a certain demand, and then we look at the bottleneck of this path. That is, we look at the edge where the capacity is lowest. And then we are interested in, is this task large or small within, with respect to this capacity? Because if it's small with respect to the bottleneck capacity, it's small with respect to all edges. But if it is large with respect to any edge, it is also large with respect to the bottleneck capacity. So therefore, the real question is, are we like smaller than delta times bottleneck capacity or larger than that? And now we look first at small tasks. So now we assume that the bottleneck capacity is large. That is, I think this might be the wrong way around. So, I mean, we look at small tasks. So the demand should be smaller or equal than delta times B of I. And in order to solve U of P for small tasks, there is actually a rather simple and really elegant method. Simply write down the LP for U of P, the most natural LP that comes to your mind. That means we have a variable xi for each task I. And then we want to, of course, maximize the tasks that we select. And for those, we want to maximize the weight. So the sum of xi wi is what we want to maximize. And then we have to ensure that the capacities are respected. So for each edge E, we look at the tasks that cross the edge E. And for those tasks, we compute xi di, so the demand, the fractional demand taken by that task on that edge. And the sum should respect the capacity that we have. CE I wrote in the other notation before we used a U for this, UE, for E in P. And then, of course, we cannot take a negative amount of a task. So what does it mean if we have this edge E and we look at this crossing, then like the fractional amounts of tasks that we take should not be too big. So here it's again UE. And if we directly round, of course, we will satisfy the capacities and expectation for each edge, but we will have like some edges where we underfill and some edges where we overfill. So that means like generally, if we like do the most simple rounding technique that we would like to do, then we would not get a feasible solution. But like I think the main contribution was in this Approx 2002 paper. It's also mentioned in this 2007 paper of those authors. You can solve U of P with rounding with alterations, What does it mean? You have basically the overall idea is you have a two-phase process. So first you do a simple rounding of the LP, and then you have a pruning phase where you correct your solution to have a feasible solution. And of course, you have to be careful what you remove in that phase, but you can do this in a systematic way, and you can make sure that you only lose some epsilon factor of your weight by making your rounded solution feasible. So the way that you could imagine it is that a single task cannot block all the other tasks. So that is, you need a whole bunch of tasks in order to exceed the capacity, and therefore you have also a large selection of tasks that you can remove. And since all tasks are small, you just have to remove a small amount, and you can average it out so that you have only a small weight that you remove. So that's on an intuitive level, and you formulate this as a random process, and then you can show that you deterministically get a feasible solution, and it's out of your given solution, and you will only lose an epsilon factor. Now the other extreme is large tasks. So a task is large if the bottleneck capacity is greater than delta times, if the task is greater than delta times the bottleneck capacity. And for that, we first look at a simple case where we have uniform capacities. That is, we have here is a 0, here is our UE for each E. And now we have this nice property. Since these tasks are large, any feasible solution can only stack 1 over delta tasks on top of each other. Because otherwise, of course, we would exceed the capacity. Each task is at least delta, and delta times 1 over delta is 1. So we would like exceed the bottleneck for that edge. Out of that, we can make a quite easy dynamic program. That is, we go through the instance from left to right, and we store all possible configurations that are feasible at a certain edge. That is, we look at the first edge, we look which configurations are feasible, so which selections of large tasks give a feasible solution for this edge. And then we go to the next edge and look what is the best combination of a previous configuration and things that we can do on the current edge. And then we sum up those weights and create weights for the new configurations that we can get at the new edge. And then we can actually forget everything that was before and just move on from left to right. So we can efficiently compute an optimal solution in this special case. Things get, of course, a bit more complicated if you have a capacity profile like this one here. And what's the problem? This task is large with respect to the bottleneck, which is good, but with respect to this edge, say, it can be really small. So this is something that you have to deal with. And to deal with that, without the framework that we developed, it's actually quite tough. And there was this paper of those authors here in Soda 2014. It's a quite amazing paper. It's also the title says amazing 2 plus epsilon approximation, where what they basically do is they create some maze of corridors that that can be traversed with a dynamic program. And this way you can deal with large tasks with general capacities and get a 1 plus epsilon approximation. So their result was a 2 plus epsilon approximation for the overall problem. Why is that? Well, you solve 1 plus epsilon approximation for large tasks, a 1 plus epsilon approximation for small tasks, and take the better of the two results. And since all tasks are covered, and for like each of the two sets, you have a 1 plus epsilon approximation, the better of the two is the 2 plus epsilon approximation overall.
So one question, what is the connection of delta and epsilon? Like, is it same or?
No, it's not the same. So you have delta large tasks, but then there are different things that you might lose. Actually, you might lose a function of delta. So epsilon will be a function of delta.
Okay, thanks.
So it could be actually quite large difference, but there's no other there's no other value getting in. It only depends on delta. Now a bit to the history of U of P. I think we can split it in two parts. The history, what happened until 2015, and what happened from 2015 on. And there are two lines of progress that people pursued. The first one is we want to have a 1 plus epsilon approximation, but we cannot get this in polynomial time yet. And therefore, we compromise on the running time. And the first breakthrough on this result was by Bansal and others. So you can see there's a long list of authors, which I won't read out completely, but I mean, you see it's many people who were involved. So they got a 1 plus epsilon approximation, but in quasi-polynomial time, and also the running time depended on the difference, the ratio between the largest and smallest task. Therefore, it was also a pseudo-polynomial time algorithm. And in this line of research, my first involvement in this problem was 2015, where we got a QPTAS, that is, we improved the running time of this algorithm, and we started to introduce the technique that I will explain in the next slides. The second line of research is we really want to stay in polynomial time, but then of course we have to compromise the approximation ratio. The first non-trivial result that I'm aware of is this log n approximation from 2009. And the breakthrough result, the first one on this was like Andreas Wiese and those two authors were involved, Bonsma and Schulz. They got the first constant approximation for U of P. And then this result I already mentioned on the last slide. They got the PTAS for large tasks, results in the 2 plus epsilon approximation in 2014. So, and now we want to explain what happened since 2015. And for that, we look at the general idea that is underlying for what is following. For that, we look at two simplifications. First is we look at uniform capacities. Why? Because I want to introduce the right way in a way to think about this problem. And the way that we always thought about this problem is we solve it for uniform capacity and for a simplified case. And from there, we have a quite standard way to get to the general result. It's technical and it always changes a little bit from paper to paper what we have to do. But in a way, it's complicated but standard. So the important case, like the real insights that brought us forward, came from the simplified case with uniform capacity. So we use uniform capacities. The second thing is we use resource augmentation. So what does this mean? We have this is our original capacity, and then we have the dotted line here. So we allow to exceed this capacity by a factor of 1 plus epsilon. And like the solution that you can see here is now a perfectly fine solution with resource augmentation, but without resource augmentation, at this point in time, you just need too much capacity. So, and our technique, like sort of a core ingredient of our technique is to say it is enough to solve the problem with resource augmentation. And from there, we have a standard way to transforms a result into a feasible result by only losing an epsilon. So for example, instead of like taking out this really large task, you can just take out some other task, and taking this out gives you like a feasible solution in this case. So this, of course, we have to do in a standardized way, in a nice way, which I will come back to. That is, to summarize, we have a framework. We develop the algorithm with resource augmentation. We apply our sparsification lemmas, and then we can buy out of the resource augmentation by spending at most epsilon opt in the cost.
Can I ask a question?
And it was not a one-time invention to have the sparsification framework. That we came up with that in 2015, and then we were able to deal with large tasks first, and then we needed to deal with small tasks, and all kinds of details changed over time. So I see the whole thing as a process since 2015 that each time got more sophisticated and more involved. And
I think
yes.
there was a question. Rahul, were you asking a question?
Yeah, I was asking a question. So this resource augmentation, can we, I mean, the other intuitive way would be to actually decrease the bar, right? 1 minus, but that doesn't work.
Decreasing all I think it's the same thing, right? Yeah, if we decrease all demands by a factor 1 plus epsilon, or we increase the overall capacity by 1 plus epsilon, it should be the same thing, right?
Yeah, okay.
I think it's just a matter of like how you technically perform all your proofs in the end, of course, changes, but essentially there's no difference.
Yes.
So what about this approach? Like, if we, instead of the capacity being 1, if we put it to 1 minus epsilon and then use resource augmentation.
So let's see. What would we get? I mean, we might really lose some part of the solution then, right? That is, say the instance is just one big task, and there's nothing else in. Then I can just schedule the task, but if I reduce capacity by 1 plus epsilon, I get 0. So then from there, if I increase it again, I have nothing. So
yeah, right.
So I mean, one thing you have to keep in mind also is this might be a special case. So there are a few things that we could think about, because if there are only very few tasks, then we are in a comfortable situation where we can distinguish all possibilities. And we really only have to really deal with the resource augmentation when there are sufficiently many tasks available. It's like you have always some DPs that are stacked on top of each other, which makes it sort of complicated to handle. But I mean, in a way, you can think of separating the instance into like regions where you can easily deal with few tasks, and then you have some other regions where you really have to apply your framework for many tasks. So I mean, this might, like maybe for other problems, in certain situations, such a thing might be sensible, but then you have to take care of that you only apply this technique if there are sufficiently many tasks available.
Sure, thanks.
So, and then a few results that I see as somewhat a direct consequence of dealing with sparsification. I mean, it needed some new insights, and it developed our understanding piece by piece. But we did not, like the core technique of those results was the sparsification. That was like a PTAS for relevant special cases, 5/3 approximation in polynomial time, and a quasi-polynomial time approximation scheme that had an improved running time. So before we had n to the O of log n, and now we have had log n. So for those results, we needed some boxes and some insights and the sparsification lemma. Now, how does the sparsification lemma work? On the left-hand side, I have the formal description. I don't really want to go through the details because it's somewhat hard to follow. I will explain it on this picture here on the right. So therefore, let's assume in this picture, just for this picture, that we have an epsilon that is 1/4. And what do we want to do? We are given an instance I, and we are given now an optimal solution because we want to show a property of the optimal solution. That is, we do not want to show an algorithmic result. We want to show that it is possible to make some space. And therefore, what we want to do is we want to compute a second solution of prime, and of prime should be almost as big as opt. And what we can do now is we can look at a special edge E. And for this edge E, we can have a specific like slack that we can create for this edge E. So this value delta E is a slack that we create for edge E. And what do we want to have now? We want to have that there are only few bigger tasks than the tasks that we remove. So that is, we want to remove tasks to make space. And if we only look at the edge E, we could say, okay, we can just randomly choose some of the tasks, say, maybe it's enough to remove that task here, and then we have enough space on this edge E. But maybe it's not a good choice because maybe for this edge E prime, it would have been much better to remove this task, even though it's more expensive, but then we have created some slack for two edges at the same time. So this is sort of the difficulty that we have to deal with. And the way that we deal with that is, right, in the sparsification lemma, we say essentially look at the 1/epsilon largest tasks. So we have that one, that one, that one, and that one, large with respect to the demand. And then what we can do is we can guarantee that we remove at least one of them. Say that one will be removed. And then this delta E that we gain is the size of the task that we remove. And this we can get for all edges, like for each of the edge, we can get it. So for all edges simultaneously, we can get this sparsification property with only losing an epsilon of the cost overall. So this is the strength of the lemma. The way it works is using a linear program. That is, we are now given an optimal solution, and we want to remove as little as possible from this optimal solution, such that the sparsification property is satisfied. That is, we want to minimize the weight of removal. Those weight removed from the optimal solution, such that, well, if we look at the 1/epsilon largest tasks that cross E within the optimal solution, then we only want to remove one of the 1/epsilon largest tasks. That is, the sum of the fractional values should be should be at least one. That is, not only one, but we want to remove at least one of the tasks. So sort of ideally, we could think of that we only remove one. That would be the cheapest for this edge alone. But then, of course, you have dependencies between these edges. So it might be that you remove more than one task, then you are super happy for that edge, but you might need it because of other edges. And well, this LP, of course, we cannot like solve integrally, but we can solve it fractionally. And how can we do that? Well, the easiest way to deal with that is to set xi to epsilon for each I that appears. Why? Because here we always have a sum of 1 over epsilon tasks. And we only look at edges that have sufficiently many tasks. The other edges we are not interested in. We don't sparsify edges with fewer than 1 over epsilon tasks. So if we do this, then for each relevant edge, we have gained a value of 1 here fractionally. So we have a very good fractional solution. It only gives an epsilon of opt. But then we can show that in this special case that we have. So like this is quite generic LP, but applied to the tasks, the way that we arranged them on the line, we have a special version of this generic problem here, for which it's known that there is a constant integrality gap. So this LP has a constant integrality gap for the type of instances that we look at. That means we get fractionally an epsilon times the weight of T star, and then we get like 4 times the weight of T star, 4 epsilon times the weight of T star as an integral solution that we get, and we can afford to lose 4 times epsilon times weight of T star. So that's the idea behind that. So the sparsification lemma, now put into context of what happened next, is we still have this top line of 1 plus epsilon approximations in quasi-polynomial time. So this QPTAS appeared on the last slide already, and then I mentioned already we improved this QPTAS, so we improved the running time from log n to log n in the exponent. In between, we also had this result here. It is a 1 plus epsilon approximation in polynomial time for special types of instances. And the most important one was if we can ensure that there exists an edge such that all tasks go through that edge, then we have PTAS. And then the second line continued. We got 5 over 3 plus epsilon approximation in polynomial time in 2018. And then finally, well, we got the 1.269 approximation and then the 1 plus epsilon approximation in polynomial time. Now, the interesting part is, so those 2 results I have not mentioned yet on the other slides because they are somewhat specific. We introduced a new technique, UFP the game. So we gamified everything and things got more fun. So they got better because we first were able to improve the approximation ratio, and there were still some things missing to get the PTAS. And then finally, we actually got the PTAS. So the remaining talk is now about how does this game work. And the generic idea is, well, we play a certain game to sketch small tasks. So we had small tasks and large tasks, and we have to bring them together. And now we always had the problem to bring together the LP and the DP. And in a way you can think of that is that we can bypass the LP and integrate it into the DP. That's the way that I somewhat see it. But first, what is the relation to the picture that we had in the beginning? So we have the street art, and yeah, well, you see there's a lot of art involved in coming up with all those specifications and everything. You can see that is we have to have rectangles that must be fitting. Also, we use lots of boxes, which I did not present. So you can think of the whole thing as a box that is filled with tiles, but there's a much nicer connection. So those guys, they started with street art and were just happy about their street art in the beginning. And then they came up with Flash Invaders. That's a game for the street art. So how does it work? So you download this app, Flash Invaders, and then you go through the streets. And when you find such at the walls, you find these artworks, you take a photo of that. And then I suppose with your GPS location and some image processing, they validate if you really found like authentic artwork. You get points. You can collect the points, and then you have like all artworks that you have found and the points that you collected from them all together. By the way, I contacted the authors, like the artists, and they gave me the permission to use the pictures in my talks. So how does the game now work? So I mean, to finish the relation, they gamified their artwork. We gamified our algorithm. So the idea is we have a player. It's a solitaire player. So that is, you don't play against an adversary. You just play in a way. And then the tasks are presented to the player in a predictable manner. So you don't know the future tasks, but or actually you do know them. But so it's not an online setting; it's an offline setting. But you cannot do anything about the future tasks yet. And what will happen will depend on some random events. So the tasks are presented one by one to the player. And the player chooses, I take this task, or I do not this task. I do not take this task. Then the small tasks are rounded. That is, with high probability, we round a task to 0, like the capacity. And with small probability, we round the demands to a very large number. So that means after rounding, we either get a 0 task or we get a large task. So that's how you can think of it. And in expectation, we get the original demand with this random process. And yeah, as I said, the background is small tasks can be handled by a DP instead of, so it's now they can be handled with a DP instead of an LP. So it's easier to combine now small and large tasks. So here's an example, and here on the left-hand side, I remind what happens, and there are also some more details. So a task I gets presented. So like in the first version of the game, they presented left to right. So we know that the start point is on the very left, and then it moves further to the right. And then what the player does, so if this is task I, the player either accepts or rejects I. If the player rejects I, then of course the demand is not taken, but also the profit is not collected deterministically. And if the player accepts the task, then the player always gets the profit. There's like no question, you get the profit. But then after the profit is taken, there are these options that either the task is large, then nothing really happens. We take the task, we consume the capacity, and that's it. Or the task is small, then we throw a bias coin. And if the coin shows heads, the demand is rounded to 0. If the demand shows tails, the demand is rounded to epsilon times the overall capacity that we have. So it becomes a large demand. And the expected demand is the demand. So how does that pan out for this example? The first task is a large task. So it's presented. So this color means it's presented. And maybe we take it, then it's in the solution. The next task is presented. Maybe we decide not to take it. Then it's out of the game. And we have a large task. We maybe also do not take that one. It's also out of the game. So until now, we only have collected the profit of this task, nothing else. Now the next task is presented, and we decide that we would like to take it. That means we collect the profit, we toss a coin. Now we were somewhat unlucky, so the task got rounded up. That is this tails event, this very unlikely tails event. so the capacity is consumed. And that's something that we have to live with from now on, and the next one gets presented. We again decide that we take it, toss a coin, and now we were lucky it was rounded down. That means it has 0 demand, even though we have collected the profit. And yeah, this could happen now again, but now it's rounded up again. So we were sort of super unlucky because 2 of 3 tasks were rounded up. But now something interesting happens. So one thing is our demand already exceeds the original capacity, but it's still feasible because we are within the resource augmentation. But the next task comes in, and now we don't have a choice anymore. Like the small task here would fit. Like as a small task, it would fit here. But then in case it's rounded up, it would exceed the capacity. And that forces us to reject the task. So we have no choice anymore because we have to stay consistent. Even in the case that it's rounded up, we have to maintain a feasible solution. So we don't have it. Now, what's the plan to show that things work out? We first play the game optimally in expectation. So in the end, we have a randomized algorithm, and the expectation things work out. And the plan is that we play the game optimally. And it's actually not hard to show. So this step 1 is sort of the easiest step. We can show that the game can be played optimally. Then we say that, okay, suppose we have a very good, so there exists a very good UFP optimum. Then there also exists a very good game optimum. That means the expected gain that we get in an optimally played game is at least 1 minus O of epsilon times the optimum that we can get without the game. The third step that we plan is we now compute an actual UFP solution from the game solution, and again we only lose a 1 minus O of epsilon. So we lose an O of epsilon and we get a 1 minus O of epsilon.
So
step
one question: what is the algorithm? You are first playing the game and getting a solution, optimal game, and then from that you are converting to a UFP solution. Oh.
So the algorithm is yes. You play the so. I'll come to that. So the basic idea. So this is not the final idea, but the basic idea behind is you compute an optimal strategy for the game. You play the game, and then you convert the solution into an actual solution. So that's the basic idea behind.
And also, is it a guarantee in expectation, or there is a concentration as well?
It's an expectation. So we were thinking of de-randomizing it, and we were not able to do that yet. Also, I think it's really an expectation. I don't think that we have high probability guarantees.
Okay.
So for playing the game optimally, we can look at states of the game that we can have. And what you can see is at any point in time, the important thing that we have is which tasks are selected and rounded up. That is a large task and the selected rounding up task. That those tasks define the states that we are in. That is at a point in time t, these 3 tasks give us a game state, and then we have values associated with states. And since all of those rounded up tasks and all large tasks are at least a constant fraction of the optimum of the full capacity, we know that there are only polynomially many choices of configurations for one edge. There are only linearly many edges, so overall we have only polynomially many states that the system can have. And then we can run a DP to like what do we want to have? So we have the states, and we would like to compute now a strategy. And what does the strategy do is, suppose we are in a certain state of the game and a task is presented to us. Then we want to have a statement, you should take the task or you should not select the task. And we want to, of course, maximize the expected profit given that, that we are in a certain state. So what, is there something missing? Yes, strategy does not consider past profits. That means for each state, you can compute what's best expected gain that you can get from here on. But note that this does not depend on the profits that you got before. Like at each point in time, you somewhat greedily want to maximize the profit of the remaining, because like you are already in the state and the past is already done. You have already collected the profit. You will not change it anymore, no matter what decisions you take in the future. So at whatever point in the game you are, you want to maximize the profit of what comes next. And to play this optimal is, well, we consider all game states, but we order them by the number of remaining tasks that that means like think of it as playing the game, as playing the DP right to left. That is, we take the last edge and look what tasks are there, and then we look how do we get there piece by piece. And if there's only one task in the game, then we can compute the expected profit for this like trivially. And then you can like go through the choices that we have from a state to selecting or not selecting the next task. We know all subsequent states and all profits of that. And then we have a probability distribution. We select the task and then we get a certain profit with a certain probability, or we do not select the task, then we get another profit with a certain probability. And therefore, we get values for all states. And in the end, we have an initial state for which we have the optimal profit. So, and with that, we can play the game optimally. We have like a fixed decision for every possible state in the game. The second step also works.
Tobias, could you wrap up in another 5-10 minutes maybe?
Yes.
Thank you.
I think, I mean, it's not so much anymore. I just do those things a little bit faster. So playing the game optimally also works. We consider all game states, and step 2 also works. That is, if there exists an optimal strategy, then the basic idea is if a task is in the optimal solution, then we select it. If it's not in the optimal solution, then we do not select it. And then showing that things work out well is based on concentration arguments. That is, recall that we have here a resource augmentation. And unlike, so I drew the pictures the way that I did because otherwise you don't see anything, but you should think of the resource augmentation to be rather large compared to the demand of a small task. And therefore, you must have a quite strong deviation from the expectation in order to exceed this dotted line on top. And therefore, you can, for each single edge, it's easy to show that like with high probability, you do not exceed that edge. And you can, so this type of argument is enough to show that if we are given an optimal solution for UFP, there also exists a very good solution for the UFP game. And then the step 3 does not really work yet at this stage. That is, the idea is we simulate an optimal player and we choose tasks that we selected, but there's a problem with that. Because if we simulate the player, we might have this specific situation. We have all those tasks. They are all small tasks, and the player just selects all tasks. And then the top task is super expensive. What does it mean? So if we now simulate the player, then deterministically we will reject that task because we have taken all those low-value blue tasks. But the player has a certain probability to get this task since some things got rounded down. So in expectation, it also doesn't get it, but there is a certain probability that the player gets this super large tasks, the super heavy task. And therefore, the player can actually have a much higher profit than the algorithm. So that said, the strategies of the player don't seem to be all too good. So these adversarial strategies, like the ones that I presented, do not seem to be good strategies for the player. Therefore, it's well possible that this idea works with real optimal game strategies, but we were not able to show that at this point. So that means just simulating the player fails if you sort of have an adversarial player which maybe does not play optimally. The first partial fix was we can box the solution. That is, we can not only like select the task, but also like enforce the task to be in a box. The boxes themselves turn out to be actually quite good because we can show that we don't only lose an epsilon factor by boxing those tasks. The problem is we might have a choice which box to take, and this can lead to some approximation loss. So in the first version of the game, which was a soda paper in 22, we got this 1.269 approximation using those boxes. Version 2 of the game, I will only go over this quite quickly now. This is the version where we then in the end were able to fix everything without the use of boxes. So we have our game, that is, we have our instance here, and we have tasks that are presented. And we toss a coin. That's sort of like in the original game. But if we round up a small task, something special happens. Like instead of going linearly from left to right, we get now some type of tree structure. That is, we get a profile that we guess here, or that we distinguish a polynomial number of profiles here. And we deal with the left-hand side of the profile and the right-hand side of the profile separately. Now we suppose that the left-hand side is done with, and then we look what happens on the right-hand side. This is the interesting part. This dotted edge has a special meaning because we distinguish, are we on the left-hand side of this edge or on the right-hand side of this edge? And now if we have a small task, that is like if it's rounded down, it's rounded down on the right-hand side. If it's rounded up, it's rounded up on the right-hand side. But on the left-hand side, we never change it. We take the original size on the left-hand side. So if it's rounded up, we have a task in this shape. Because this structure on the left-hand side allows us to keep a precise profile and deal with that in polynomial time. The problems appear on the right-hand side, but on the right-hand side, we do the rounding. Yes, so it's like the way that we got to this game that in the end works. It's more really a technical thing. We solved the technical problems that we needed to get there. I mean, there's not a very clear intuition why it should work, but I mean, it's like a much more complicated game that just happens to work in the end because we can basically the problems that we had to deal with is that the left to right order of tasks in increasing starting time is different from the right to left order in decreasing starting in decreasing times. So now the 3 steps that I was talking about from version 1 completely go through. We can still play the game optimally. we get game solution in 1 minus O of epsilon of the optimum. And now in the more complicated game, we also get a 1 minus epsilon approximation that we wanted to have. So those steps, here's some illustration of why things work out now. In the new game, what we can do is, like, if we have this type of bad situation, we essentially have the possibility to remove tasks from the beginning instead of tasks from the end. So that is, in a way, you can think of it, we have a mechanism to remove tasks that are cheap and that have appeared beforehand, and removing those tasks makes now space for the super expensive tasks. And this is essential, like one of the essential ingredients why the new game now works and we get the solution that we want to have. I conclude my talk with open problems. I think sort of the next problem to look at is, do these techniques that we develop for UFP work for SAP, for the geometric version that appeared in the beginning? So a 2 minus epsilon for is known for, like, so this 1.9 something approximation is known. And we know that many UFP techniques work for SAP. So can we actually get an improved approximation or a PTAS for SAP too? Then, of course, do our techniques work for other geometric packing or covering problems? And as a final open problem, all those techniques like stack on top of each other and things get quite complicated. So the stock paper from last year has 80 pages. If you take the full version, we are currently working on the journal version. And the question is, can you get some other approach like an LP approach, or can you get a strong simplification of the whole thing? That is, if you can get a much simpler PTAS, I think that would be a perfect candidate for a conference like SOSA. So thank you for your attention.
Thank you so much for the talk, Tobias. Maybe we can take some questions now.
Yeah, I have a couple of questions. So one is it's a dynamic, this DSA problem, dynamic storage allocation problem. Do you think this techniques might be helpful there as well, or have you tried?
Dynamic storage allocation problem is the one where you do not have a capacity bound, but you want to minimize, yes, right?
Like a strip packing version, strip packing.
Yes, so I have not really been working on that. We borrowed some techniques from those papers. So like when it comes to packing tasks into boxes, a lot of the technical background was developed for this dynamic storage allocation problem. I think long time ago we were thinking also of improving things for dynamic storage allocation, but there was nothing really coming out of that.
I see. And the second question is it known to be W1 hard, this problem? I mean, is PTAS the best, or you can actually go for EPTAS or something?
Actually, I never looked into that. There is, Andy Wiese was working on parameterized algorithms for UFP that I know. So
yeah, I think it is. Maybe it's W1 hard.
Yes, okay. I would not be surprised, to be honest. But I mean, the things I would have to look up myself.
And like even for simple case, when you have, as you mentioned, uniform capacity, does it, like this game, is it simpler then, or like is PTAS is simpler?
The game is the very same. And also before our result, what was known for uniform capacities was not essentially better, or I think it was not better at all than what was known for general capacities. So what happens is for uniform capacities and for constant range of capacities, basically things behave the same for us. So like a constant range of capacities doesn't really make a difference. And then from there we can like create some regions, like some exponentially increasing regions that we look at to cover all capacities. So what's always difficult is you have this smooth transition from one region to another, and therefore you have to do some complicated things to combine those regions. But basically, the general capacities come from the sparsification lemma. It's like in this and to the log n paper, we tried to unify this sparsification lemma to have something called bonus UFP. And then we said, we showed that if we can solve bonus UFP, then with uniform capacities, then we can solve UFP with arbitrary capacities. But then it turned out that for the last step of the game, we still had to change a few things around, and we had to unwrap the entire framework again. And in the end, in the write-up, it makes the bulk of the writing to generalize it to general capacities. But technique-wise, the real ideas are in the beginning of the paper for uniform or like constant range of capacities.
Last question. So these techniques are mainly for the path case, but if you take tree, for example, unsplittable flow on trees or general graphs, does it like, I think log n was the best one, I guess, previously. So was there any improvement on those cases for trees?
Log n I'm actually not aware of. Log square n I know.
Or maybe, yeah, polylog, some polylog was not, maybe
yeah, log square n. So, I mean, I have been thinking about the tree version a lot, actually. So getting down to log n would be really amazing. Its constant is open, I think. I think there is it's APX hard for trees. If I recall it correctly, constant might be possible. So, but log n would be sort of what I would be aiming for. But the techniques that announce so the integral, so yes.
I guess small jobs were not a problem for tree. It's similar, I guess, if the jobs are small, but large jobs are problematic.
It's somewhat always a problem to combine large and small, right?
No, I'm saying, I mean, you can separate them out and get. I mean, my point is whether it's only the large job one is to focus. I mean, the log square and bottleneck, is it because of large jobs? Because for small jobs, maybe you can use similar LPs and get a PTAS or something small factor.
So the hard instance of Friggstad combines large and small ones, and they somewhat it builds a tree that exponentially branches, like the branching becomes exponentially bigger. So I think for this integrality gap, I think it gets out some log somewhere. I'm not sure. So it always it has leaves, and then the tasks in the leaves like go up, but in the parent edge, the small edge of the leaf is a big edge. No, it's actually a small edge. Another big edge is coming in, like a big task is coming in that combines with all the small tasks from all the leaves. And then this structure somehow repeats to the top. So you really, for the hardest instances that I know for the tree, you really combine large and small tasks heavily.
So sorry, another question is the integrality gap of the LP, your result does not say anything about that. So, or does it say something about the integrality gap of the canonical UFP LP?
I mean, the integrality gap says only something about this LP, right?
What? Can you repeat?
So the integrality gap only says something about the specific linear program.
Yes, yes. So I'm just really... because people have studied the linear program a lot. So is it known to be, I mean, because of the PTAS, whether do you have some ideas whether it's really a small integrality gap or like 1 per epsilon integrality gap, or it's not clear?
The point is, even a constant would be a major result for the trees, and a constant was known a long time for UFP.
No, not trees, but general path only. Or general UFP path. Path only, path. I mean, the same problem that you studied for the LP.
For the integrality gap. Well, I mean, you know that there exists an LP because you like every DP you can transform into
No,
an
no,
LP.
I understand. My point is the canonical LP that you wrote in the beginning, for example.
The
That is already
LP
bad.
for small tasks, that does not work anymore if you have large tasks.
Yes.
No.
Okay.
I don't know what's the integrality gap. I think it might be unbounded.
Okay.
Or no, I don't have a concrete number in mind right now.
Sure. Yeah. Thanks a lot.
So do we have any further questions? Okay. If not, then I'd like to thank the speaker once again and conclude the session. Thank you everyone for attending.